All right, thanks. BirdNet and beyond. That's what we call it. And I think that's a good like title to kick off this season of Bioacoustics. I'm here with Stefan, the other Stefan on the BirdNet team, Felix and Tom, and we've just like introduced some of the things that we've been working on regarding the analyzer packages, whatever that means, and then agile modeling. And so the outline for this presentation will be that I will start with what's new, what's next on the BirdNET Analyzer, and then Stefan will take over and talk about our Python package. Felix will talk about the R package for that can run BirdNET in R, and then Tom will close off with some words on agile modeling and embedding search. And so thinking about the analyzer, I think um, this was last year, so this is what I call how it started, and so this is me talking about the vision that we developed. And if you still remember, like there were two things. We wanted to be the most sophisticated tool for terrestrial audio analysis, and we also wanted to be the go-to tool for researchers. And so this vision hasn't changed. But quite a few things have really happened, and we've really tried to achieve this vision, or at least work towards achieving it. And so this is how it's going, and I think um, these screenshots and numbers like speak for themselves. We published the BirdNET Analyzer, and people started using it. And I just really want to like briefly highlight a few things before it gets too confusing on this slide. So first of all, we had like quite a few interactions with people who are using it, bug reports, feature requests. We closed 199 issues, um, which is, I think, yeah, pretty cool. Not all bugs, also some features. Um, we have more than 1,000 unique visitors within 2 weeks on a GitHub repository page. So that's not like, yeah, like consumer software. This is targeted at researchers, and I guess this is pretty unique for a web page on GitHub to receive that many visits. There are quite a few people watching and subscribing to it. There's 142 forks. So there's other people tinkering around with the software. There's 28 contributors who have actively contributed code to the repository. So it's not just us. This is like a community effort. And then again, also, and this is thanks to everyone who's listening and who's downloaded, there's more than 8,000 downloads already on the installer, which is pretty cool to see that a software package that has been released a year ago has seen that much traction. All right, and so people are actually not just downloading it, but also using it. And so what I've done is try to maintain this project map that you can find at birdnet.cornell.edu/projects that lists all the projects that we are aware of where people used BirdNet to do some sort of acoustic analysis targeted nature conservation. And just to give you a few examples, of course, people have been working with birds, um, clocks, nutcrackers, for instance, specialists like specializing on certain seeds. And so when the trees are gone, the bird is gone. And so if you restore the forest, the birds are coming back. That's pretty interesting. Of course, then people have done breeding site attraction, which is pretty cool. And I've seen there's some folks from the Vogelwarte in Switzerland are here. So this is a project that Felix's company, Ökofora, has been working on with them, trying to emulate breeding sites for common terns and attracting them, and then using BirdNet to see if the birds are actually coming back. People have used BirdNet for anthropogenic sounds, which is pretty cool. So this is beyond birds. There's an engine detector in the BirdNet model, and then this was a project in Yellowstone National Park where people try to assess what the disturbance of snowmobiles are and how that impacts the birds. And then again, beyond birds, people have also done American toad monitoring, which is pretty cool. So there's a few insects and amphibians and other classes that people are using BirdNet for. And I think the the ability or like the feature that allows people to retrain their own models for their target species has really accelerated the use. And I can just like encourage everyone who's listening, if you work on a project and want us to put your project on the map, it comes with the names and then the location, even contact details. And if you have a paper to kind of like advertise your project that you're using BirdNet for. There's a form. You can take a look at the GitHub page, and even at the project maps at the bottom, it has like a link that leads you to the tutorial on how to add projects to the map. And then just to mention it again, because I always like just to show some faces of people who work within the BirdNet team. And so there's Connor and I leading the team, but then the rest of the people you can see on this page, this is just the German team, or like the team based in Germany. So this is all, yeah, these are all people focused on the technological development of BirdNet. And then Connor is also supervising a number of ecologists who are working on the ecology side of things. So there's developers like Joseph and Max, mainly responsible for the analyzer, Felix and Stefan, who are here today for the Python and R package, Daniel, who's focusing on the API and our backend services, Maha and Melissa, who are our AI researchers developing models, and then there's our app development teams, Sarah, Raya, and Amir, and then we also have some embedded systems engineers, just newly hired Friedrich, and then John to work on TinyML for smart recording units. Just to give you like an idea on how many people are actively working on advancing BirdNet here in Germany. All right, and so something I really like to mention, since the BirdNet repository has grown and the number of people who are using the analyzer is like beyond our wildest dreams, it can be tricky and hard to really listen to everyone and push updates and fix bugs. And I just wanted to highlight a few things on how you can reach us. What's the best way if you have an issue or a bug or something and you want to just like convey this to us. And usually the first place you should go to is the GitHub issues tracker if you found a bug in the analyzer or you have a feature request. So this is the place to go, because then the people working on the analyzer will actually see it and can implement the changes. There's a discussion forum also, which is like if you don't have a bug, but just like a general question, or you need some help with troubleshooting, or you just want to participate in general discussion, that's the place to go. This is usually a place meant for members of the community helping each other, talking about these things, and us occasionally taking a look at these things. If you want to contribute code, which is always welcome, please make sure to make a GitHub pull request. There's a Reddit forum, which is completely unsupervised, at least like none of the BirdNet team members is actually supervising and moderating, but there are quite a few people actively engaged in general discussions, so that might be a good place to start. And then, of course, you can always send us an email, especially if you want to ask for collaboration. And then usually, if you send an email to czb-birdnet@cornell.edu, it'll be Ashik who's going to reply and then relay the information if needed. All right, so what's new in the analyzer? What has happened in the past almost 12 months since the last BioAcousTalk? And then you might have seen that if you download the analyzer, you can scan the QR code or go online. The most recent version has been released yesterday, so Max pushed an update. It's version 1.3.1. Quite a few things have changed. We added some things to the GUI. And one of the things I really want to mention is there's now also a installer for macOS. So you can download a package version for Windows and macOS, and that should ease the install and the setup process quite a bit. It's still in beta, but again, make sure to give it a try. And then if you find an issue, let us know in the issues tracker. And of the things that are new, I want to focus on two very specific things in my presentation today, and that's the newly added review tab, and that's the language settings. And so to get started with the review tab, if you click on the review tab, this is what it looks like. And what it does is it lets you verify detections. So let's say you did the batch analysis of 10,000 hours of audio, you got a bunch of results for a number of classes. You just want to know how well you did. And so the way to do this until now was to go through Raven and Raven selection review, and then going back and forth between Raven, and then eventually go into R and then get the regression curve to figure out the cutoff thresholds. But now the one thing you need to do after you run the batch analysis is you have to extract the segments, and segments are randomly selected detections in a 3-second window. These will go into a folder sorted by species, and then you can click on the review tab and start the review. And so the first thing you're going to do is select the segments folder, where all the randomly selected segments are. Pick a species that you want to annotate or at least like validate. And then you'll see for each of the snippets, 3-second snippets, you'll see a spectrogram and you can play the sound. So that lets you inspect the sound visually, and then even by playing back the sounds and listen to it, and then you can validate. You can say, okay, yeah, that's true. That's a true positive. That's a false positive. You could even skip and undo if you need to. And then the most interesting thing, if you go on and do that, and you just realize this is like a really rapid way of reviewing things, and it's quite fast, because usually you can just like at the first glance at the spectrogram, you can instantly see if the species is in there or not. And if you scroll down while you're annotating, you'll see this regression curve. And this is something that we implemented based on the paper that Connor and I put out, which is called the Guidelines for Appropriate Use of BirdNET Scores and Other Detector Outputs. And what it will do, it'll try to fit a curve among all the true positives and false positives, and then tell you the cutoff threshold. So let's say in this case, if you say, okay, for my use case, I need 90+% accuracy, you'll have to set the cutoff threshold at 0.82. And so as you go, you'll see the regression curve, and then at one point you can probably even stop because it's not improving, and then you get like a better understanding, okay, what's the cutoff threshold that I need to use to achieve a certain accuracy. All right, and then the other thing is that we now support multiple languages. There's 4 at the moment, and you can click on the settings tab, and then in the drop-down menu, you can select a certain language. But there's also ways to actually change and contribute languages. And I just want to like briefly walk you through the process, how that works. You first need to locate the translation files, which are a bunch of JSON files that are in the install folder under internal and lang, and then create a new one. Let's say in this case, we want to add the Spanish translation to it. It has to be a JSON file, and then go into the English JSON file, copy all the contents, and then start translating, and you'll see these key value pairs because it's JSON, and so the key just like identifies the interface item, and then after that the value, that's the translation. And if you translate bit by bit by bit, you can then restart the GUI, and then it will show your newly added translation, and then the GUI should be translated, and then of course ideally share it with everyone else. You can send us the translated file via email, or even better, make a pull request and then submit a new language. All right, and then just briefly to wrap up my part, what's next, what's on the horizon. And so there's been an ongoing effort to add more non-birds to BirdNet, and we finally figured out like a good way and a good data source to do that. And so with BirdNet version 2.5, we're going to add a couple of hundreds of non-birds to it, and this is set for roughly like late 2024. There's BirdNet 3.0 on the horizon that will finally support variable input sizes. So you're no longer stuck with a 3 seconds and 48 kilohertz sampling rate. And we also want to support all of the bird species and then all of the non-birds that have been added so far, and that's set for roughly early 2025. We're in the process of hiring another AI developer who will like take this on, and then as we do publish 3.0, we'll also publish the entire training process and the entire training code for the big model. So whenever you're interested in, hey, I don't want to just retrain BirdNet, I want to train like the big one, there's going to be a code repository that has you covered. And then of course, we're actively developing the Python and the R package, and that's something you hear about in a minute. And then Tom is also going to talk about like Agile modeling and what that means and how we're going to integrate that into the BirdNET Analyzer GUI.
Yeah, okay. Thank you. Then hello from me. I was developing the Python package in the last month, and I want to present to you today like the features and the capabilities, and also the next steps of the library. So next. Next slide, please. This was one. Yeah. So we published the library already on PyPI, which is the common third party repository for Python. And you can download it just by using pip install BirdNET. And basically it detects the species based on the audio files and is not able to train currently. So it's just for the prediction. So on the next slide, I will show you the functionality. So we implemented two methods, one for predicting the species based on the audio files. So what you can do is to detect the species in one file. And you can also detect multiple files at once using threading. I will have some benchmarks later in the presentation to show you some differences and to get a feeling on what parameters you should use and if you should either use a CPU or GPU. And then we have also methods for predicting the species based on the location. So this is the meta model, which uses the longitude, latitude, and the week optionally. So you can also combine both models together, for example, to first predict for a specific location the species which occur there in the area, and then use the audio prediction and filtering the results with the location species. So then there, if you install the library and import BirdNET, for example, and try to predict the species in the audio file, the model is automatically downloaded, and this works also for all platforms, Windows, macOS, and Linux. So it creates a app data folder and saves the model there. So you don't have to handle any of the URLs or any of the GitHub models. It will be automatically downloaded. Also, we will support all future versions. So currently it's just version 2.4. So this is the newest version. And yeah, you can run the model on the CPU and also on GPU. And yeah, one of the main things or features is that you can read you read the audio file only in chunks and not the whole file. And this makes it very memory efficient because you only read the 3 seconds chunks at once. If you have a batch size, for example, of 8, then only 8 chunks are being read, and then this takes not so much memory like reading the whole audio file. And also it's possible to run the library using the outputs from the BirdNET Analyzer. So if you have an own model, you can export it and use it in the library to predict other species and what you've done in the model. So next slide. So I will show you some basic excerpt of the code. Like this is the main function for predicting the species in the audio file. And you see all the parameters like minimum confidence, batch size, overlap. So you can define the overlap and band passing, sigmoid activation. And there's also the species filter where you can define the location species, for example. And with the custom model, you can define like the Raven model or whatever. So then the next slide. So this will show the result, what you get. And the library is constructed in that way that you can process a large audio file, for example, like 24 hours, and you get the immediate results. For example, so it's a generator, so it will return the first interval, and then the predictions for the first interval, like 1 to 3 seconds in that case. And this will be returned immediately. So you can iterate to the whole file without having to wait until the whole file is processed. So the output only contains the species which are above the confidence you defined in the method. So yeah, that's basically the output. So next slide is the prediction of the species based on the location. And yeah, just basically, as I said, like latitude, longitude, and week. And output is also on the next slide. And it's basically the list of the species and then the confidence on how probable it is that the species is occurring at that location. So the next slide, I will show you some benchmarks. And for that, I will explain you at the experimental setup I had. I created an audio file which was 60 minutes. It's a wave audio file. And these 60 minutes had 1,200 3-second chunks. This is, you can keep this in mind because in the next slide, I've displayed some of the batch sizes and also like if you process the whole file at once. So this is like batch size 1,200. So just keep that in mind. So we tested on the M2 SSD. We had like 8 cores and 16 threads CPU. GPU was a Titan RTX with 24 GB of memory and was tested on Linux with 64 GB of RAM. And we cleared the cache before each experiment so that, yeah, we try to have the same environment for each experiment. Yeah, we hope that it will catch most of the things which are influencing the experiment, but yeah, it's still difficult to reproduce the exact same results due to many different things which influence the experiment. So, and one thing was also to set the thread count for the TF Lite model, which was the CPU model, and for the protobuf model, which was also available, which is available as CPU and GPU model. So we use these both commands. Yeah, that will be relevant in the next slide. So this is the benchmark. So what's displayed here? Like you have, we have 3 models: the TF Lite model, the protobuf model in GPU and CPU version, and the x-axis displays the number of threads we used. This is only relevant for the CPU models, so TF Lite and protobuf CPU, because for GPU there is no CPU threads, which you can see also in the bars that they have all the same height. And on the y-axis is the duration of the analysis of 1 hour, so like the 1 hour file. And what you can see is that the GPU takes the shortest time with the batch size 100. And the TF Lite model takes the most time to process 1 audio file. So there's also no advantage in increasing the batch size over 100 for running it on a GPU. And generally, it's also for TF Lite, it also makes it slower. So 100 seems to be a very good batch size for that type, like if you run it on GPU or CPU. And also the protobuf model performs better than the TF Lite model. And the protobuf model performs better if you use the automatic settings, which is like if you don't set it in the what was displayed, the commands in the last slide, like set the interoperability parallelism threads. If you just don't set it, then it performs the best. Of course, it makes it difficult to compare it with your system, so that's why I included also one thread and 4 threads. So, but there's not so much difference between 4 and auto. So, yeah, that was for one file. Now to the next slide, which is for multiple files. I tested it with 4 files, like 4 1-hour files and 4 jobs. So using 4 CPU cores. And what you can see is that the time is as fast, so that the duration of processing one file on average is as fast as like running it with the GPU from the previous slide. So it takes also only 24 seconds to process the 1 hour file. And also there's not so much difference between all these models here. So one thing to note is that it's not possible. So I used two different multi-threading approaches. In one approach, this is called version 1. There you share the same model on all threads as a global variable. And for the version 2, you initialize for each process, you load the model in the process, which takes up much more memory. But with that, it's possible to use, for example, 4 TF Lite threads, which is not possible for the first version. As you can see in the x-axis force, there's no bar for the TF Lite version 1 because that was not possible. So that's a limitation. Yeah, also the batch size on 1 was the fastest, which is different to the previous run on 1 file. So that's also interesting. And on the next slide, I will have a conclusion on that. So yeah, for the single file, the GPU is the fastest. The protobuf CPU model was faster than the TF Lite model. And it's good to use a batch size of 100 and choose the threads automatically by the system. And there is also no large RAM required because only the chunks are read, and so that's easy processing. And for multiple files, it's different. You can use the protobuf CPU model or TF Lite model with batch size 1. And so that means if you have at least 4 cores on the CPU, that seems more effective than the GPU. And so it's better to invest in more cores probably than in investing a high GPU. For example, I've also run a test where I run 16 threads, like processes on 16 files in parallel, and that took 12 seconds per hour recording on protobuf and TF Lite model with batch size 1. So compared to 24 seconds on a GPU, it's like twice as fast. So one downside is that you need a large RAM. The 64 gigabyte was full with batch size 1. So I think we have to investigate more why that is, and yeah, doing some more benchmarks. But this is like the preliminary result here on like a small benchmark. Yeah. Now wrapping it up with the future plans. We plan to integrate the library into the analyzer. For example, the reading of the audios in the chunks. Currently, it's a different method used in the analyzer. So this would be, I think, the next step. We can also improve the multiprocessing and implementing the version 2. The version 2 is currently not shipped in the library, only version 1. But we set all the parameters of the methods according to these optimized values here. So if you just use the methods without changing anything, you would get probably a very good result. So you don't have to fine tune as much as, yeah. I mean, you can still do some benchmarking, but it's ready to go. Also, one thing is to return also the embeddings and not the predictions of the models. And also supporting multiple output formats, for example, like CSV output driven selection table or hoplite database. And maybe one thing is also interesting is to optimize the multi-threading approach into like splitting several files into different parts and then processing these parts on parallel. And this for that, it's required to be able to just maybe to analyze a file only from a custom start and end. So yeah, this also plays in hand with if you have a large data set and you want to predict and takes multiple days, then you can stop it at any time and start it again so that you have a custom start of each file. That's basically this point. Also supporting low resource environments like on the Raspberry Pi, like providing in the Int8 model. Also supporting prediction of live audio streams also on the Raspberry Pi, for example. And yeah, we're also debating if it's useful to include the model training into the library, but it's still not clear what's the concrete what we should include in the library and what's like part of the analyzer. So that's still like like discussing points. And yeah, so you can check out the GitHub repository and also like testing it, trying it, submitting new code. That would be very helpful. And with that, I will pass it to Felix, the R package.
So, are you seeing the presentation? Yes, okay, great. So, hi, I'm Felix. I'm happy to talk to you about BirdNET R, the R package. And we thought about this for a long time, but now it finally happened, thanks to the work of Stefan, because BirdNET R is basically a wrapper around the Python library that we have here. But it should allow you to integrate BirdNET into your R workflow. And I would say it is about time. So Stefan already showed this. One of the first goals that we set ourselves was to have that BirdNET will be the go-to tool for researchers focused on bioacoustics and conservation. And with this being one of our main audiences out there, we realized that R is, like, for many ecologists, the main and sometimes the sole language, the sole programming language that they use for their data workflows. So developing BirdNET R is part of our overarching goal in the BirdNET Plus project, to make automated sound ID as easy and as accessible as possible for ecologists, researchers, and of course, everyone else. The goals for this package is that you do not need to learn any other programming language, right? You do not need to learn Python. It should fit into your existing R workflow, so you don't have to go outside to a third-party software. And I include here the BirdNET Analyzer. Even though it is great, it should be possible that you just stick to your data workflow, and it should feel very familiar to our users. So using Python under the hood gives us some advantages, but also some challenges that we have to deal with. Like the main advantage is that we have a single code base. We can, if we implement a new feature, this is the place where we implement it, and then we can port it to our library. We don't have to double our code. We don't have to double our maintenance effort, and we probably don't double our bugs. So this is a good thing. But it also comes with some challenges. The first is that we need to automate the setup of a Python environment that works for everyone. And we don't want to burden it upon you that you have to do it. So because we encounter a multitude of systems, like the different operating systems, the different settings that you have, the different Python versions that you have installed, this might be pretty error prone, and I expect some bugs. So the same here, please report them to the GitHub page, and I will show you the link later. And implementing the technical details is not so much of a problem. Under the hood, we're using Reticulate, which is a great R package that interfaces Python and R. More of a problem is translating from the Python style into an R style. So Python usually uses the object-oriented programming, whereas R style is that you are used to is more like a functional approach. And designing a consistent API that is familiar to our users is not that easy. So I want to give you an example. On the left side, you would see Python code where you have a class. It's the model, and then you have a method that you use on it, and it's predict species with an audio file. But this is not how we do it in R, right? There you would expect a function, predict species within audio, and then you have an argument where you pass the model to. Or the output that Stefan showed earlier before on the left side, when you use the BirdNET library, with reticulate in R. On the left side, this is what you get, where you have like a nested list where the list names are the time intervals and the species names, and then you somewhere get the confidence interval. The confidence, this is not really what we want in R. We want a data frame where every variable is a column and every observation is a row, where you have the start and end time here, the scientific name and the confidence. This output is something that you can then use with the tools that you're familiar with. So let me give you just a quick walkthrough through the Get Started guide of the BirdNET R package. So it's still in its early development. It's trying to follow the BirdNET Python package, of course. And I'm not going to explain every function and every function argument, just that you get a feel how it might look like. So first of all, for the installation, you need to install Reticulate to interface Python. And for now, it's only available from GitHub. So you need to install DevTools, and then you can install it from GitHub, which is also outlined in the docs. To set it up, you call the library as usual, and it will check for a valid Python version and if you have already set up your environment. If you haven't, or it's your initial setup, you call the helper function, install BirdNET. And I took some liberty to get inspired by the TensorFlow R library, which does it like pretty much the same. And this creates a default virtual environment with Python installed. It's called R BirdNET. And if you don't have any need to customize it, then you should be good to go. This should work out of the box. It will install the Python package and all its dependencies. If you want to customize anything, you can either specify your own virtual environment name, or you can specify a path to a virtual environment, which might be useful if you want to add it to an existing virtual environment. The only thing you then have to do is to tell Reticulate that you want to use this environment. So with everything set up, it's time to identify some species. And the first thing you do is to initialize a model. We have a few arguments here where we can customize it. You can set the threads and you can set the language in which you want to have your labels, in which language you want to have your labels. So as you can see right now, there's nothing that you can specify which model you want to use, or if you want that you can use a custom model. This will come in a later version. Right now, it's not yet implemented, but it will be probably available in the next version. Of course, you need a path to an audio file. BirdNET R ships with an example file, so if you want to play around. And then it's as easy as calling predict species with the model, the audio path, and you can set all the arguments that you have seen in the talk before with the bandpass filter, the overlap, and so on. This is then the end result that you've already seen. A data frame, variables are the columns, the observations are the rows. And this is the output that we're used to, that you can then use your favorite tools to further process. And to outline this a little bit, I want to show you how you can use a custom species list. So in this package, a custom species list is just a character vector. And you can either specify it yourself, like you see on the top, or you can also use the meta model, like Stefan showed, predict species at location and time. You type in your coordinates and your week, and it will give you a list of species that are likely to occur there. And that custom species list you can pass to the argument filter species, which you can see at the bottom. And this will then limit your results to the species list, and in this case, also to results only above a confidence of 0.3. But you don't have to do it in the predict species function. It's designed to fit into your workflow. So you can pipe the results of the predict species function with this piping operator. I don't know if you have seen it, but it takes the output of the function and passes it into the first argument of the next function. And you can use your favorite filtering functions like dplyr, filter, and you can look for the common name should appear in this list, and you can filter with confidence, you know? So this is then quite common R stuff that you can perform on it. So one note on the labels, because this is something that I found usually pretty opaque in the BirdNET Analyzer, is that you do not necessarily, it's not easy to find which classes are available, which species are trained on, and which languages it supports. So I have added an helper function. It's called available language. It does what it says. You can check which languages are available. And to if maybe you want to look at all the labels, all the 6,000 plus labels to check if a certain species is in there, you can use the helper function get labels path, because it just lives in a text file somewhere on your computer. And to make it easy, use this function, specify the language that you need. You get the path, and then you pass it to a helper function, get species from file. There's nothing fancy about it. It's just to help you. And then you will get all the labels with the scientific name first and the common name in the language that you specified last. So this should make it a little bit more transparent on what classes you can work. And I think there's still room for improvement, but this is already a direction I'd like. So to round it up, I want to talk about the scope of the package and what's coming next and where we want to go with it. So it's intended to be simple. We want you to code your data workflow, and we won't take away much of it, right? So we want to provide the tools that bring you from audio to species ID, and we'll probably stop there. So it's a wrapper around the BirdNET Python package, and this is where the functionality comes from. But if you're like me, you're probably thinking, well, isn't that a great place to put like my data analysis pipeline code that I can share with the world, maybe have this cool visualization? Shouldn't that be part of like a BirdNET package? And I'll definitely agree with that. And I would love to see such a package. And this is why we propose like a community maintained R package. This can be a collection of tools. It doesn't exist yet, but it could be a collection of tools that go beyond classification, that starts where BirdNET R stops. I called it BirdNET Extras. We can call it whatever we want, but this could be a place for a Shiny app for validation, for example. This could be the place to implement code for classification metrics. This could be the place to test different thresholding methods, for example, to convert scores to probabilities or to add code for occupancy modeling, whatever ecologies out there need. But this is out of our scope, and this is something that the community should pick up. We might kickstart it though. The next steps is to definitely stabilize the API. You can expect some breaking changes in the next weeks and months. But if that has stabilized, we try to publish BirdNET R to CRAN, that it's even easier to install. So that's it from me. Check out the GitHub page, BirdNET team/BirdNET R, and thank you for listening.
So this is going to be a little bit of what we've been up to on the Google side, and that we're hoping to get into BirdNET in some form in the future. And I'm going to be really fast to try to respect folks' time. So Agile modeling for bioacoustics. Sort of our motivating question. I'm Tom, I'm from Google, and I'm here to help and all that. Is how do we build a system to efficiently answer questions which nobody's ever asked before? And this is sort of the problem we run into all the time. People want new classifiers all the time. They're looking for new things in their data. And so we basically looked at like, what is the life cycle of a passive acoustic analysis problem, where you've got some data collection, you've got to get your training data together, you train a classifier, you look at the output of the classifier, decide it's crap, and then go back to step 1 or 2 again. And repeat until you're happy with it. Then you run some inference. And then finally, you can start answering those ecology questions that we actually care about, right? And when we look at this, all of this stuff in the middle is actually really stuff that we can really optimize as computer scientists and as machine learning folks, and try to really, fix that workflow and make it as quick and painless as possible. And so we've got a few strategies that we've hit on to really like make this as painless and fast as we can. So first, we use a pre-trained model to get some embeddings. You might have heard about that previously. And what those embeddings let us do is it lets us search for relevant examples, which lets us collect training data much, much, much faster than you could through linear scan or looking through like select files where you might have an idea that the bird is there or whatever it is that you're looking for. Once we've got some of those relevant examples, we can train a small classifier. And as we train that classifier, we can look at the outputs, validate on the fly, and then iterate. So, hey, those things that we said yes, yes, no, that becomes the next round of training data, and train up a new version of the classifier and repeat. And maybe the most important part of this is that because we're working on these pre-embedded data, search is really, really fast. And training a classifier is really, really fast. So we can actually in under a minute, have a new version of a classifier and start putting results back in front of you. You can evaluate. And then another minute later, after you've done some evaluation, have another version of the classifier. And usually we're finding within just a couple rounds of this, people are getting more or less what they're after. And so if everything goes according to plan, our workflow starts looking a little bit more like this. We collect our audio data, we use the ML stuff for a little bit, and then we get on with our actual goal of answering those ecology questions. So I'm going to sort of just go to a bit of a demo because I think that's probably like the easiest way to kind of see what we're getting at here. So late last year, we released this project with the Australian Acoustic Observatory that enables search over into their 2 million hours of audio that they've collected. So we can pick out an example. I'm going to pick one of my all-time favorite birds, the eastern whitbird, which sounds like this. Oh, let's see if sound works. Sweet. Yeah, great. So there's our eastern whitbird. And then we can select a 5-second window. And then we can search for that. And what it's doing is we're now computing the embedding, uploading that to a server in this case, computing the embedding, and then getting the results back from all of this Australian Acoustic Observatory data. And what we see is a whole bunch of eastern whitbirds. And I'll sort of filter that just a little bit. And we can look around and we can see that we're getting eastern whitbirds even when there's, mixtures of a lot of stuff going on here. And, it might be that we find really interesting examples like this one. So that second note is a female response to the male, right? And hey, that's behavior, right? So then we can start looking for that and say like, hey, let's now do a search for that and start surfacing results for that particular behavior. So female response to male. And then we could, conceivably, if we had a little bit more UX with us than just this site has, start building a classifier around that. So here we have a female response, here we don't, that one we do, that one we do, and so on. And so then that becomes training data for a classifier. So search is really fast. Training the classifier on these examples that we select is pretty much as fast as well. And so we can iterate really, really quickly on new questions. So what underlies this is really like having this embedding model, which can be Perch, or it can be BirdNET, or it can be other embeddings as well. We pick one that seems appropriate for our problem, and then we put the embeddings into a database. And then we work with that database for doing search so that we can surface examples readily. Oh yeah, here's a good search example. See like this sort of woodpecker drumming in the background, even in these really muddy ones. And then we can evaluate train classifiers and so on. So late last year, we released a Agile modeling collab notebook where you can basically play with this in Python and sort of get some validation workflow and all of this. But what we find is that folks really hate looking at Python code and really hate trying to get Python environments working on their machines. We're a tiny research team, and it's amazing that the BirdNET Analyzer BirdNET team has such a great crop of developers. So what we're really hoping to do over the next while is move some of this functionality into BirdNET and make it readily accessible to the community that way. I think everybody that we've had working with the Colab notebooks, the folks that we can sort of get over that hurdle, have said that this is really transformative to work with. I think one of my favorites was Mary Clapp saying that they have to like force themselves away from working, from building new classifiers to like go do their actual day jobs at the Institute for Bird Populations. So I feel like we're achieving what you might call product market fit or something like this. So really looking forward to working with Stefan and the team to bring a lot of this functionality to BirdNET over the next year. Done.
Wow, that was perfectly on time. We brought it home. Thanks, you four. That's quite a way to end that presentation. I can't even imagine what life would be with a search function easily accessible. So I think we have a few minutes for questions. And I also wanted to highlight that in 2 weeks, we will be changing topics to focus on detection range and why detection range matters and how to calculate detection range for forest bird species, and then also beyond that as well. And we'll be with Dominika, I think Winiarski from a research institute in Poland. And so that'll be next Wednesday, or in 2 Wednesdays from now. So first, I see Alexander has his hand raised. And yeah, feel free to talk, Alexander. I got you unmuted.
Okay, can you hear me?
Yes.
Yeah. Thank you for the chance to ask a question. Do you think that actually I have a problem with my research now because the species is not found on the source, like from the Sinocanto and others. So how to identify these species, because this species is really how to say that, like the cryptic species in my location right now, and also endemic. So it's really hard to find these species. So that's why I'm looking for the sound, and it's really hard to find out. So do you have any recommendation from other source like Sinocanto maybe, or others, because I never seen these sounds of species. Uh, however, for the how to say it, like not really scientific, I found this video. I mean, this species on the video on YouTube. And is it possible to input the YouTube source into the BirdNET maybe, or like a Raven Pro? Because the video is only 2 that I found the species, the snoring rail. Thank you.
So for the video part, I think there are download tools that let you download just the audio from YouTube. And then once you have that, and if it has a bunch of calls, that sounds like the agile modeling process. And so Tom, do you want to take this question on what to do if you only have 3 or 4 instances of a sound?
Yeah, so I think what I would do in that case, like embed the data that you have from your study. In cases where you really don't have, if you've got 1 or 2 examples, it's like, yeah, we search for that, see if we can find some similar examples within your target data, and then start labeling those. So we're really like setting up the agile modeling workflow as a way to start from very few examples to get to what you're after. Other things you can do if you don't even have a recording of what you're looking for, it can be a good starting point to start by searching for something that just sounds similar. So if you've got a similar sounding class, even if you don't have search yet, like using detections for a similar enough sounding species can get you over that like initial hump of trying to find some of your target data. Really common thing that happens in camera traps, for example, is like, oh, we're looking for like hyenas, but it turns out we've got lots of training data for dogs. And that's sort of close enough that if you search for dogs in this hyena habitat, you start finding lots of hyenas.
Okay, okay. Thank you very much.
Thank you, Alexander. Does anyone else have any questions for the team? We've got one from David, which is there a way to contribute training data for target species from passive acoustic recordings to the public BirdNET model, and would that be helpful?
I was just trying to start typing, but it's just easier to just answer like this. Yes, absolutely. If it's annotated. And so the interesting thing is that what we've done in the past is every time we have a data set that has been annotated, and usually that's rate and selection tables or some sort of like, boxes around calls, we've put these on Zenodo and published them so anyone can use it. And that would be my preferred way of accessing these data. So if you have a data set and want to go through like the process of cleaning it up a bit and making sure all the labels are consistent, and then boxing calls, Zenodo is a great place because then you can get cited. You'll receive a DOI, and then you also have versioning whenever you want to update it. And that's definitely a place we look for new training data on species that are missing to include in the BirdNET big model.
I see we've got a question from Taiki. So I'm going to go ahead and get your microphone working. Let's see.
Yeah, so working. Looks like I was allowed to unmute.
Yeah, we can hear you. How's it going?
Good, thanks. Thanks for the great presentation, everyone. I think this is probably mostly for Tom. So I work with marine mammals, so very similar enough, but different to bird recordings. So I guess in terms of trying to use that agile modeling approach, that to try to do it for marine mammals is going to require some sort of baseline thing that's been trained on a lot of different marine mammal species, which to my knowledge probably doesn't exist yet. Is that right?
Well, we did recently release a coral reef adapted version of the model. It's called Surf Perch. And that's trained on a combination of coral reef audio, free sound, and birds, which we found for the coral reef data sets we were looking at. That combination actually outperformed training on just coral reefs, and also like just birds outperformed training on just coral reefs as well, which was really interesting. So these things are really transferable. I also, I know someone's made a novel marine mammal detector for a particular marine mammal using this workflow as well. So one answer is like, hey, we've got this surf perch model that's sort of already adapted to underwater sounds to some extent. Features transfer really well. So the best thing to do is really just go try it and see how it works and then complain to me if it doesn't, because then we'll really be motivated to help. And then finally, like the sort of way that we've been setting this up, and I think BirdNET Analyzer is moving in the same direction, is having some flexibility about exactly which model you're using. So if you've got a model that you know is really well adapted to underwater, being able to sort of plug that into the same workflow is, shouldn't be too difficult.
Cool. That's awesome. I guess one small follow-up to that. So for marine mammals, we have everything from sounds down at 20 hertz to, the awful things up at 140 kilohertz where they're clicking. So have you tried experiments with these like vastly different sample rates and it still seems to translate fairly well?
Yeah, so this was actually some of the motivation for the reef work. So we've tended to find that if you have target signals that are in the ultrasonic range, if you sort of mess with them through some combination of resampling and frequency shifting to get it into the audible range, we tend to do a great job. Things are pretty sparse up there. And then for really low frequency stuff like the raw bird model, embeddings tend not to be great if you frequency shift those up into, sort of a higher range where there's more birds. And that was the problem that actually led us to doing the coral reefs, because a lot of the fish sounds are sort of in the lower frequency range. So it might be that if you're looking at signals that are really like crossing a number of these frequency ranges, you might want to break them up one way or another, so that you can sort of look at like, oh yeah, here's something for the ultrasonics, here's something for the audible range, here's how we're handling really low frequency stuff, but also just go try surf perch and see how it does.
Cool. Thanks so much.
Yeah.
Thank you. Why don't we take one last question, and this will be from Tiago. And he is asking, are there any other search methods besides similarity and active learning that you found to be useful?
So I guess what's the right way to go? So ultimately we're looking at vector search here, right? So vector search over embeddings. So there's a lot of ways you could search. There's a good argument that like template matching, spectrogram template matching is another thing that you can do. And that is a kind of search as well. So like, what's the activation of this template with all of this target audio? The thing that's really great about vector search is that there's over embeddings is we've got good embeddings that like are able to sort of work well even when you have overlapping sounds, which spectrogram matching has a hard time with, template matching has a hard time with. And furthermore, there exists a lot of existing libraries and tools that let us do vector search really, really quickly. And so we're able to leverage that and get to a good place faster. And then active learning is sort of its own giant set of topics. So like, what are good ways to go about that? And a good chunk of what we're doing on the side is basically figuring out like, what are the best ways to get the active learning workflow running in such a way that you guys don't have to worry too much about the, exactly how the sampling methods are working and things like this. To answer as briefly as I possibly can.
Groovy. All right. Well, thank you, Tom, Stefan, and Felix. Super exciting. And yeah, we'll have to have you back at least in 1 year to see just how far we've come. So thanks everyone for tuning in, and until next time, take care.
Thank you so much. Thanks, everyone.